Alright, so today we're going to be coding a OS kernel from scratch in C and assembly. We'll start by coding our own bootloader. Since we'll be focusing on the kernel, I'm going to write a very simple bootloader. I'm going to set up a virtual machine that will have 2 physical hard disks. So the C colon disk will be just 512 bytes, and that will contain the bootloader. And the only task of the bootloader is to load the kernel, which will be on the other disk. That way we don't have to worry too much about file systems at this point. We're going to add support for writing to the screen and reading from disk by using BIOS interrupts in real mode. And then we're gonna get into protected mode by creating a global descriptor table and setting up segmented memory. And then we're gonna focus on getting the interrupts to work. So, exciting project. Let's begin. What's up, guys? Welcome to today's show. So, today we're gonna code our very own OS kernel. That's kinda cool project, no? Let's just start by setting up the basic project. Alright, so we're gonna code this project in C and assembly. It's going to be as much C as possible, but some things, especially in the beginning, needs to be done in assembly. So to help us out a little bit, I'm going to use a library that I coded a while ago. It's called asm stdio, and you can find this at the repo. I will put a link in the description. So this contains a printf style function, but for assembly. So there's a 32-bit version and a 16-bit. So you can download these, and inside an empty project directory. So you download the include directory from the repo, and it looks like this. So before we begin, I'm just going to go in there. I'm going to delete the 32-bit version, and I'm going to go into the stdio.h. And I'm going to define that we were going to use the 16-bit version, and we need to change this 4 into a 2. And now it is ready to be used. Alright. So I have opened up the project inside of VS Code, but inside of the main OS kernel we're going to create a makefile. We're going to start by just defining a few of the things, and we're going to build on this later. So let's say that we have some flags, and we're going to have some C flags as well, and some linker flags. And let's see here. The first thing we need is a bootloader, and I'm not going to put too much work into this one because we're going to focus on the kernel, but we need to load the kernel somehow. So I'm going to create a simple design for that. So we're going to make a loader.o from loader.asm, which we will create. And we're going to compile this by running nasm, so you need to download that package if you don't have it. So the flags are the assembly flags, and the C flags is the C flags. And this will create the object file. When we have that object file, we want to create a loader img. We're going to use LD to link. I think I'm going to put the LD flags inline here because we're going to use the LD flags variable primarily for the kernel. So I'm just going to reference a script file, which I'm going to call loader.ld, and then I'm going to take the source and provide an output file like this. And I also want to truncate this. So this means that we're going to fill it out with zeros, so it is a multiple of 512 bytes. The block size is 1 and the count is 512. this is only temporary until we have a kernel. And we also need some memory, so I'm going to use 16 megabytes. And all is going to be loader.o. So inside of this OS kernel folder, which is the main project folder, we're going to create loader.ld, and this is going to be pretty short. Okay, so what sections do we need? First of all, we need to define our base memory address 7C00, because that's always where we boot, right? And then we're going to have a text section. And let's see if I remember the format. I think it's like this. So this says that every code section should go in here. And we're going to have one more, which is data. And here we're going to have the data section, but we're also going to have the BSS and the read-only data. And this is so the C code is going to work properly. And I think this is it. Let's save that. Alright, so now let's start creating this loader.asm. So instead of OS kernel, we'll create loader.asm. Bits is going to be 16. And we're gonna have a start label. First thing we're going to do is jump into that start label, and then we can include the stdio.h. And let's set our stack here as well. We're going to change that later on, but for now this is fine. So let's just initialize all the stuff we need. So we need to figure out where the code segment is. So let's move into AXCS and then move that into all other segment registers. So we need it in SS, we need it in ES, and we need it in DS. So CS is a code segment, this is the stack, this is an extra data segment, and this is the data segment. And by the way, let's move this down here. So directly after we have set up this segment register, we want to set up the stack. So let's move into stack pointer or stack label. And now I think we should be able to use my printf. So let's do something like this. And let's just do an endless loop here. So let's say halt and then loop, no up, and then we jump, loop. Okay, but in order for this to be a proper boot sector, we need to end by defining a word which is 0x AA55. I think it's in that order. And we need to make sure that this is 512 bytes total and that this is at the end. So we can do some scripting here. So if we take, let's see here. If we take 510, so that's the whole file minus this which comes after, and this is 2 bytes. So 512, and then we minus, let's see here, if I remember, so the current address minus the starting address. So the starting address is up here, the $, and the dollar is this line. So the difference between those two is the number of bytes here. So we remove them, and we have removed these since we don't start at 512 but 510. So this is standard stuff for a bootloader, and we just need to fill this out with something. So let's add a byte of zeros. Okay, I think this is correct. Let's see what it says. So let's run make line 20. Oh, I missed one parentheses, didn't I? Oh, this shouldn't be loader.o, it should be loader.ing. Cannot find loader.o. Right, I forgot to add, we need a flag here. So we need to say that this should be an elf, because I make an elf object file out of it, and then I link it into a flat binary. Now I think it's going to work. Okay, looks right. And we have our loader.img at 512, and I have an alias which is objdump86, which will show a 16-bit assembly, and we work at that level because every computer boots up at 16 bits, so we need to code for that. So I have made this alias. So you can just, if you just write this line, then you can just do objdump86 and provide loader.ing, and we see the whole thing right here. So let's see. So here we have our jump, so we go to 1AF, that's our starting point. And all this code is the stdio library. What did I say? 1AF, right? Right, so here is our code. And here we see call3, so that's on the top here. That's our printf function. And this is this is the string that we're printing. And then we have our halt, or no up. Right, so we jump to 1D1, and that's here. Yeah, and then we have the endless loop, and by the end we have this 055A. Okay, it looks right. Let's see if it runs. No graphics. Maybe it's Singularis. Hello world. It works. Alright, so now we have a very simple bootloader. And in order to break out of this thing, what you do is you press Control A and then X, and it terminates. So Control A, release, and then X. Alright. So our next step is to load this this kernel. So I decided that we only have the bootloader 512 bytes on the primary C: hard disk drive, and then we have the rest here. Since we're limited to 512 here, this is a pretty good setup, and we don't have to worry about file systems at this point. So we will just read in the entire disk and put it somewhere and execute it. So that's the general idea. And in order to do that, we need to use a BIOS interrupt, which is a special set of routines which will help us read from the disk without having an operating system yet. So this is called, let's see, BIOS int 13H. So I think I'm usually use this one. So here we see all the different disk options. Each of these is a system call. And what we need is read disk sectors, I think. Let's see. Right. So we just fill in all of these, and then we execute the interrupt. And as you can see on return, it's going to put the error status inside of AH, and it's going to set the carry flag if we have an error. So maybe we can take this on, and let's say that this is the end. And here we have read disk. So let's just paste it in like this. And let's see if I can make all of this. Nope, I don't have that. Let's see. I want to make this a comment. On my other machine I have keyboard shortcuts for this kind of stuff. Maybe we can use the command palette. If we search for comment, add line comment. There we go. Alright, so we just fill in all this stuff. So AH should be 2 and AL should be the number of sectors to read. So let's move into AH 2 and move into AL. And here I'm going to have a constant, which is the num sectors, which we are going to define. And then we need to specify the track and cylinder number starting at 0. And since we're reading it from the beginning of the disk, it's going to be 0. And one sec, my mouse ran out of battery. And CL should be 1. So we can move into the whole register, and we're taking the high number, which is 0, and we're taking the 1. And then we need the head number, which should be 0, and the drive number, which is, the first disk is 80, and the second is 81, and we're going to use 81. So we move into DX, the head number and the drive like this. And then ES and BX is going to contain where we want to write this to. So let's see here. Since we're in real mode, it always boots up in 16-bit real mode, which means that in order to reference a memory address, we use a combination of two 16-bit values. So one of the segment register like ES and SS, those we used in the beginning, and then an offset of BX. So what we do is, if we, for instance, have ES is equal to, let's say, 200, and let's say BX is something like, I don't know, 50 maybe. So what will happen is, it's going to take this ES register and it's going to shift it 4 bits to the left, so 1 hexadecimal digit, so this becomes this, and then we add this 50. So this will be the final memory address at this point. And this is almost what I want to use. So I want to put this at ES 200 and BX 0. So this will create the address 2000. That's where I want to put my kernel, at least, the first stage of the kernel. Okay, so instead of moving into ES here, AX, let's say we move BX 200, and we use BX here instead. So at this point we only need to clear out BX, which we do like this. Okay, so now we have filled in all of these. Now we just need to first we need to clear the carry flag, so we are sure that we can detect the error properly. Then we run the interrupt, which is 13. And now we need to check that carry flag. So let's see, we can do let's say jump if carry to error, and otherwise we jump to end. We'll have this error here. So let's print some message, or let's do it like this, because AH will contain the status if we have an error. So it will contain the status code. So it would be interesting to print that out. Let's see here. Yeah, let's do it like this. Let's call this endless instead. And here we're gonna put end. So we jump if we don't have an error, then we jump to end. So if we're at the end here, we can move into AH. We can zero out AH. Because we don't have an error. And then if we do, then we're not going to do anything, but we want to exchange AL and AH. So we just flip those two, because I want the error code to be inside of I want it to be in the lower part. But maybe we should clear AL as well. Yeah, let's do that, because that is not very interesting. So here we jump to error. And then we want to print some message. Let's print the error code. So let's say that ax is equal to %x, and we provide ax. So this is how we use the macro. So it's a printf style. It works really well for hexadecimal numbers at least, which is what I use the most. Okay. And then we can fall through down to endless here. So let's see if this fits inside of 512 bytes. That's not very sure. By the way, I came to think of one thing. If we run this, we want to make sure that we have cleaned and that we have a loader ing. Num sector is not defined, that's true. And I'm going to create a script which figures that out on its own, but for now let's create a static file. So inside of our include here, let's have a config.h, and here we'll just have num sectors equals 1. And let's include that inside of here. Clean this up a little bit. So this error, times value minus 11, is negative. That's because we have overflowed our 512 bytes. So we need to remove 11 bytes somehow. Maybe we don't need this hello world message. Okay, that's better. Let's try it out. Let's not dig into this now. I guess we'll figure it out later. But we can just print, let's see. Let's rewrite this to a little bit simpler. So we jump to error. And then we just print f error, and we jump to endless. Otherwise, we just fall through to endless. So if we have a carry, we jump to error. Otherwise, we jump end. I'm not sure if we can have another printf. We'll probably overflow. Let's try. It worked. Okay. So we successfully read all that stuff. That's good. So now we just need to execute that code. So let's see how we do that. Well, all we need to do is we jump into that memory address. So we do a far jump to this 2000 address where we have put the stuff. Like so. And now we need to create just a simple kernel so we see that it works. So let's, inside of OS kernel, we create our, I'm gonna call this xkernel.asm, because I wanna differentiate between assembly files and C files, because both will create .o files and that can conflict. So assembly files will be prefixed by X, except this loader, because it doesn't have a C version. The loader is ASM only. Alright, so the kernel is 16 bits. Jump start. We're gonna have our stdio. And now we do need to initialize the registers. So move AX CS. So CS at this point is still going to be 0. Yeah, then we don't need to do this. Let's just print F kernel successfully loaded. And that's many characters, but now we don't have to worry about that, because in the kernel we have as much space as we possibly need. And then we can hold and let's have an endless here as well. Something like this. So we need to create a linker file. So let's open up this LD file and copy everything. And we create kernel.ld, paste it in. And the only thing we're going to change for now is this prefix. Now we're working at 2000 instead. So let's update our makefile. We can put it inside of LD flags here. So our script is going to be kernel.ld. So we're gonna have a kernel.o from kernel.asm. Gonna compile the same way as the rest. Like so. by the way, now we can delete these two lines. Let's see, kernel.o, and then we need, no, it's not called that, it is called xkernel. And we want to create a kernel.img, and we're going to have a lot of dependencies here. So let's say we have one variable containing all the assembly objects, so x obj, and we're going to have an c obj, which is empty for now. So let's say c obj is empty, x obj is only one right now, which is the xkernel.o. And we're going to run our linker with ld flags. We're going to provide all our input files, which is what this means. Then we're going to create an output file, same as before. We're going to change mod. And we're going to truncate the same way. So it's a multiple of 512, because each sector that we are reading in has that size. Alright, so when we create the loader, we also want to make sure that we have a kernel. Like so. I think this is it. Let's see if I forgot something. This should be jump. Cannot open linker script file. Kernel.ld. What did I call it? Kernel.ld. Did I misspell it or something? Let's resave this. Okay, there it is. Must have been something wrong with the file transfer. Alright, so let's see. Now we have a kernel.img at 512. And if we do an obj dump kernel.img, we will see that in the beginning we have this jump to 1af, which is here, and then we have the printf code and the halt. So let's see if this works. Kernel successfully loaded. Alright, so now we have created our bootloader. That's all there is to it. And now we can put our focus into the kernel. So we'll be right back after this.
Did you learn anything useful today?
and you want to support this channel, go to drbirch.com/support. You can also click the button Become a Member. Thank you for your support. Alright, so let's begin by creating a new file, kernel.c, inside of our main project folder. And here we're going to include kernel.h. And let's create that inside of the include folder. So kernel.h. Pragma once, and inside of here I'm gonna include, instead of having one std_int.h and one std_lib, etc., I'm just gonna have an std.h with all of that inside. So I'm gonna create that too, std.h. And inside of here, I'm going to put the integer data types, and they are not very many, since we are working in 16 bits. So we have an unsigned char, which is int 8. We have an unsigned short int, which is int 16. And then I'm going to define some aliases to convert between these data types. So this is going to go to int 8 star, and this is int 16. And maybe that's enough for now. Yeah. And inside of kernel.h, we are going to define our main function, and it's going to be a void main, like so. And this we will create inside of kernel.c. So void main, and let's say we print some message. Let's say hello from C. Let's just do this. And then return. By the way, we should never return from this function, because this is our whole operating system. So instead we can just do an endless loop by the end here, like so. And by the way, we don't have any Boolean types, so let's create those as well. So I'm going to define let's see, an unsigned bit int of 1 bit is going to be a boolean, and then I will just define false as 0 and true as 1. Easy enough. Okay, so now we have this, but we need to have some interaction between our assembly code and our C code. For instance, this printf function is written in assembly. So inside of, let's see, where do we want to put this? I guess inside of std.h. So let's first say that we have a void, I think it's underscore printf16, and it takes const int 8 for the format string, and then some arguments. And then I will just create a macro where I say that print f of args is equal to underscore printf 16 of args. Alright. And let's make one for putchar as well. And this is just called putchar 16, and it takes a constant 8. Okay, and we need to export them. So we are importing it here inside of xkernel.asm. So let's export them by doing global printf 16 global putchar 16. Something like this. And here we want to call main, which is external to this. Okay, something like this. So let's go into the make file and take care of the compilations. So we're gonna have a kernel.o from kernel.c, and we want to run cc with some c flags -c input file. And I want to make a list. I've already started. So for the kernel we want to compile xkernel.o, and we will also have some C objects. So here we'll have kernel.o. And it's important that inside here that the X objects are first, because we need the assembly code to execute first. By the way, since we are working in 16-bit mode, we need to add, on top of everything, even on top of the include, we need to add some inline assembly code. So we need to say that this is a code 16, and it's a data segment. Like so. And this we need to do for every file in 16-bit mode. We can close the loader, we're not going to use that now. Okay, looks good. Now we need quite a lot of C flags. So I want to have some error reporting. I will not have any optimizations because I don't want it to alter my code when we are this low level. We're gonna need dash f freestanding. We're gonna need no std lib, since we don't have any C standard library when we are working at the operating system level. What else? We need to disable the stack protector. What else do we need? machine is 16 bits. We need to use our include directory. Do we need anything else? Let's see here. Let's start there anyway. Let's see what the compiler says at this point. Maybe it's no hyphen. So just like this, maybe. Okay, that's one of them gone. No stack protector. I don't like that I don't see the whole error. Why is that? That's weird. I hope they didn't change something in the latest GCC, because that would be unbearable. I'm not sure if it should be the W that it suggests. I think that that's two different things, but let's try. I'm not really sure if this is necessary anyway. Right, that differs in signess. Since we're working with our own integer data types, we need to specify this macro that I did. So that's why I made them, because we need to do that quite a lot. Okay, everything compiled, but will it work though? Let's see. No, it did not quite work. Alright, you guys, now I think I know what's wrong. If we look at the files we create, kernel.img, it's 1K in size. And if we go to include and we check config.h, we only read in one sector, and one sector is only 512. So when as the kernel grows, we need to update this so our bootloader reads in the right number of sectors for the kernel. Later I'm gonna make a bash script which automates this, but for now I will just change it manually. So this is all it takes, I think. So let's see. Now it works. Hello from C. So now we are able to code C for our 16-bit operating system environment. And we have achieved a lot of things today, so I think this will be all. I really hope you liked this episode and that you wanted to subscribe and watch the upcoming episodes in this series, because we'll do a lot of fun. And in the next episode we will create the global descriptor table and interrupts. So thanks for watching. Thanks for tonight.